Thank you, Bob. Thank you for that introduction. And I'd like to thank the organizers for inviting me here today. And what I'd like to do for the next few minutes is to give you a broad overview of hyperpolarized-gas MRI of the lung, both touching upon the capabilities of this technology, but also looking at some of the broad factors that are shaping the field, which don't have a lot to do with the technology, but I think it's still interesting. So what I'd like to do for the next 50 minutes or so is cover these topics. And I want to start out talking about motivation, or another way to look at this is, why should I care about hyperpolarized-gas MRI? So the motivation really comes from the fact of the still high impact of lung disease on our society. Let's start by looking at chronic obstructive pulmonary disease briefly, or COPD, for which the major cause is smoking. This is now the third leading cause of death in the U.S. It affects tens of millions of adults, both in the U.S. and worldwide, and the national cost is estimated at approximately $50 billion. Another very important disease, which I'm sure all of you have heard of, is asthma. Asthma currently affects about 20 million adults in the U.S. and almost 10 million children. It is, in fact, the leading cause of school absences for children from a chronic illness. And it has a current estimated national cost of almost $20 billion. The last disease I'd like to mention is CF, or cystic fibrosis. This is the second most common life-shortening inherited disorder in children. It affects about 30,000 in the U.S., but there are 10 million genetic carriers. And although this disease affects quite a few less people than either COPD or asthma, what's very devastating about this disease is that even with the advances in the past few decades, the median age of survival if you have CF is still less than 40 years. So it's a very devastating disease if you have it. Now next I'd like to touch upon what we do to look at these diseases. The standard clinical mode of care to look at lung disease is still pulmonary function tests, or so-called PFTs. Here in the picture, we illustrate a person doing so-called spirometry. The pulmonary function test includes spirometry, body plethysmography, and DLCO. One thing we get from spirometry, and I mention this because you'll see this number pop up in a lot of the slides later, is so-called FEV1, or forced expiratory volume in 1 second. This is how much air you can breathe out if you try as hard as you can in 1 second. The advantage of these techniques is they provide functional information about the lung. Specifically, we get information on ventilation and gas exchange. This technology is relatively inexpensive and widely available, and it's easy to administer. But it has a big disadvantage. And the big disadvantage is that it provides no regional information about what's going on inside the subject's lung. This means that inherently it's insensitive to early disease and insensitive to gradual progression. In some subjects, there's also an issue with reproducibility. Now, there are several clinical imaging modalities that have been used over the past several decades to look at the lung. The first of these, of course, is X-ray computed tomography, or CT. It has the advantage, has very high spatial resolution and good temporal resolution. CT is widely available in almost every hospital, and it's quantitative. You get the tissue density in Hounsfield units, so you can get a quantitative evaluation of the lung tissue density, which can tell you a lot of things about what's going on in the lung. Probably the primary disadvantage is, of course, it involves radiation by nature. This is a limitation for longitudinal studies or for pediatric studies, and as you may have heard, over the past few years there's a heightened public awareness about the potential dangers of radiation, and so this has become a bigger issue with CT. Although the spatial resolution is very good, it's not as high as the alveolar size, so you can't look at what's going on individually at the alveolar level. It's also challenging to obtain direct functional information, although you can infer functional information from certain measures. I should mention there are some research things that are being developed that will let CT do better in the lung. For example, dual energy CT scanners are now commercially available, and if you use those together, for example, with xenon gas, you can learn some very interesting things about lung function. And there's also other developments, for example, high-speed 3D imaging of the lung with over time, and this is something we're going to hear about in a talk later in this workshop. The next modality I'd like to mention is nuclear medicine. As opposed to CT, or in contrast to CT, it provides direct functional information, both information about ventilation and about perfusion-ventilation mismatch. It's also widely available. Like CT, it involves radiation, so also a limitation for longitudinal pediatric studies. But unlike CT, and you can tell from this nuclear medicine image, the spatial and temporal resolution are quite poor, and it provides very limited structural information. The final modality I'd like to mention is something I've spent a lot of time working on, and that's proton MRI. Proton MRI, like CT, has pretty good spatial resolution, good temporal resolution, and of course one of the big advantages of proton MRI is its very flexible contrast behavior. Like CT, proton MRI is widely available, but unlike CT in nuclear medicine, it does not involve ionizing radiation, so that's a plus for it. But the primary disadvantage of MRI for looking at the lung is that the proton density in the lung is quite low, only about 25% of the soft tissues. We also have the problem that there's millions of air tissue interfaces in the lung, which disturbs the magnetic field. And when you take these two things together, you get quite low signal from the lung parenchyma, the lung tissue itself. You also get negligible signal from the air spaces because you don't pick up any MR signal from the air. And so in healthy lung tissue, and there's fairly healthy lung tissue at the bottom of this section, what we see is a fairly low signal. What we see at the top of this happens to be a subject with cystic fibrosis. And what we're seeing, all the signal up here is actually mucus in the lung from the cystic fibrosis disease process. So proton MRI has fundamental limitations, although I should also note for this modality, there are things being developed now that are going to help the applications in the lung. For example, there have been a lot of advances lately on ultra-short echo time imaging, which gives you a lot more signal from the lung parenchyma, and there's other advancements. For example, there's been some recent interesting work using inhaled fluorine gas, so you can directly look at the air spaces using that. So what I want to summarize from this first short section, motivation, is two things. First, we see that there's currently a high health and societal impact from lung disease. It's really a problem that we need to address better. And there's a clear need for improved regional quantitative assessment of lung function and structure, either through development of another modality or improvement of the modalities we have. So with that in mind, the next thing I'd like to talk about for a few minutes is the capabilities of this technology, the capabilities of hyperpolarized-gas MRI. Or put another way, what can I learn about the lung using hyperpolarized-gas MRI? Before I get into some specific examples of this, I'd like to give a little bit of review of where the signal comes from for those of you who don't do MRI or don't do hyperpolarized-gas MRI. So we remember that in conventional proton MRI, the signal comes from the nuclear magnetic moment, so the so-called spins of the protons in water molecules, in fat molecules. Whoops, sorry. The signal strength is determined by the alignment we get, or the so-called nuclear polarization of these spins, when we put the subject or the patient into the scanner magnet. This alignment is proportional to the magnetic field strength, which is typically called B0, and the polarization that we obtain, as illustrated in this little diagram at the bottom left, is only on the order of a few parts per million. In contrast, with hyperpolarized-gas MRI, the signal comes from the spins or the nuclear magnetic moments of a noble gas. The ones that are typically used are either helium-3 or xenon-129. Helium-3 is a rare isotope of helium. The standard form of helium, as you probably know, is helium-4. And as illustrated in this diagram on the right, it comes from the decay of tritium. On the other hand, xenon-129 is a natural component of the atmosphere, and naturally occurring xenon has 26% xenon-129. Now, in comparison to conventional MRI, our polarization for hyperpolarized-gas MRI does not come from the scanner magnet. It comes from an external laser-based device, what we call a polarizer. An example of one of these polarizers is shown here on the lower right. And since we use this external device to create the nuclear polarization, the signal strength is independent of the scanner magnetic field strength. The other important issue is that we can get polarizations approaching or on the order of about 50%. So remember how this compares to what you have in a typical MRI experiment. This is about 100,000 times bigger than what you get with proton MRI. This is so large that it compensates for the low density of the gas, and we can get high-quality images of the lung air spaces by using these agents. Now, the way that you typically do this type of procedure just has a couple extra steps compared to conventional clinical MRI. Is first, of course, you have to polarize the gas using a device such as the one shown here. Depending on the nucleus and depending on the type of device you have, this can take anywhere from tens of minutes to a few hours to prepare the gas you need to do imaging. Once you prepare the gas, you have to administer it to the subject in some way. The simplest thing you can do, which is very effective, is simply dispense the gas into a plastic bag, then give it to the subject, and the subject inhales it. Once they inhale it, you can use a variety of MRI pulse sequence techniques and acquire images such as those shown here. Now, with that background information in mind, I want to show some examples of the kind of information we can get. With helium-3, these types of techniques have been developed for looking at ventilation, microstructure of the lung, oxygen concentration, and pulmonary biomechanics. In the interest of time, I just want to show you some examples from the first two, looking at lung ventilation and lung microstructure. So the simplest way for us to look at lung ventilation is a static method where we simply look at the distribution of gas following inhalation. So the subject breathes in the gas, holds their breath, and then we acquire a fast breath hold acquisition using a so-called gradient echo pulse sequence, typically. If we look at the healthy lung, we see something as we see on the lower left. We see a uniform distribution of the gas throughout the air spaces of the lung. But in subjects with lung disease, we see these characteristic, what we call ventilation defects, meaning places where less gas goes or no gas goes. For example, if we look at these subjects, either smoker, subject with cystic fibrosis, or COPD, we see all these areas where the gas either doesn't go completely or doesn't go at all. Some other things we can do is look at dynamic ventilation imaging. That's looking at the gas as it flows into or out of the lung during respiration. This is done using repeated acquisition, typically with a low flip angle gradient echo type pulse sequence. This is analogous to the type of imaging you see with cardiac MRI when you do cine imaging of the heart motion. We can also look at air trapping in the lung. And lately in humans, there's been work on developing more quantitative techniques to look at ventilation. For example, the gas washout rate. This is an example from the Sheffield group where they looked at the gas washout rate after inhalation in a healthy subject. And people are developing methods for quantitative or specific ventilation. This is a type of ventilation that the lung physiologists like to look at. These techniques already exist in animal experiments, and now they're being developed for human experiments to look more quantitatively as opposed to just a qualitative picture of ventilation defects. Now, ventilation imaging has been used to look at a number of important disease conditions, including the three I mentioned under the motivation section. And in the next couple of slides, I just want to show you some examples of the type of data you get using hyperpolarized-gas MRI in these diseases. First, we have an example. This is some work from the Robarts group where they looked at ventilation imaging in COPD, specifically looking at 15X smokers at baseline and 2 years later in quantifying the ventilation defects. What they found is that there was a significant change in the defect volume or defect percentage over this 2-year period, whereas there was not a significant change in spirometry, specifically the FEV1 measure. And here's a couple examples of some of the subjects they looked at. For example, on the left, we see this subject imaged at baseline and 2 years later, and you can see a number of the defects really in the same places but got bigger over time. And in this subject, the ventilation defect volume went from 23 milliliters up to 44 millimeters over that period of 2 years. Quite a significant change. Another disease that's been looked at a lot with ventilation imaging, and actually one where we've learned a lot about this disease that wasn't known before, is asthma. This shows a series of different asthma subjects at baseline. They have a range of spirometry. Just to tell you, 100% is considered normal. If you have larger than 100% FEV1, that's supernormal. That's better than the average person. And so here we see people that have actually supernormal spirometry down to quite bad spirometry. And we see that in general, the number of ventilation defects increases as the spirometry gets worse, as you would expect. But you also see things like this person has very high spirometry, but they still have quite a few ventilation defects. Another important thing that was learned about asthma that wasn't known is that asthma is a very focal disease. Before these types of results were available, it was still uncertain whether it was a diffuse disease that affected the whole lung or a very focal disease that reoccurs in the same place. And hyperpolarized gas imaging has showed us it's a very focal disease that reoccurs in the same place. We can do some other interesting things. For example, in asthma, look at provocation and treatment. This top one is an example of a subject who has exercise-induced asthma. And we imaged them at baseline, before exercise, and then just after exercise. And you see upon exercise, they have a tremendous loss in their ventilation capacity due to the exercise-induced asthma. Here's an example of treatment. This is a subject at baseline that has quite poor lung function, and then if they're treated with albuterol, they ventilate a very much larger fraction of their lung. This next example is very interesting. This is an example in cystic fibrosis. This is a particular subject that has what's called a G551D mutation, a particular mutation that occurs in cystic fibrosis. And this shows the effect of a drug, a very interesting drug that essentially cures the cystic fibrosis disease process. So we see them imaged at baseline, and then after 4 weeks of taking the drug. Now, certainly their lungs aren't normal after 4 weeks, but I think you can appreciate they're tremendously improved. There's lots of regions within their lung where the ventilation looks almost normal. Then when you take them off this drug, their lung goes back very much to looking like it did before they were on the drug. This next slide shows a little bit of quantitative information from some early imaging trials with this. These are 4 subjects, and in red we plot the spirometry results, and in blue the defect volume is measured by hyperpolarized-gas helium imaging. We see these are complementary to each other, but the changes you see with the hyperpolarized-gas measurements are in fact much larger than you see with the spirometry measurements, which are good because we're getting a lot more information with the imaging measurements. And one thing I want to mention about this drug, which actually has an amazing effect on these subjects, but unfortunately it's only a small fraction of the cystic fibrosis subjects. It's only about 4% have this particular mutation. But this drug was just approved by the FDA last week. The final ventilation example I wanted to show is a dynamic case. This is going to illustrate a person with a lung transplant where it's healthy versus going through rejection. And there's going to be a dynamic on the left. And what it's going to show, I'll show you what you want to see so you can pay attention. There's a transplanted lung on the right-hand side of the view and the native lung on the left, which has COPD. And so what you'll notice is that the air will flow first into the transplanted lung and then later into the native lung. See, first into the healthy transplanted lung, and then later we can see this very diseased lung, very small percentage of it is ventilated. Now what we're going to contrast this to on the right is a person that had a transplant but is going through rejection. And so what we'll see both that the transplanted lung now looks diseased. We do not see a nice, healthy lung outline. And also we'll see that the air flows into, or the gas flows into both lungs at about the same time because of the change in properties as the lung goes through rejection. We see now both lungs fill at the same time, and this lung does not look anywhere like this transplanted healthy lung did. So the point about this is you can analyze these types of results and learn something about what's going on with the physiology of the lung by analyzing the temporal dynamics of the signal changes as the subject inhales and exhales. Okay, now I'd like to move from ventilation to talk a little bit about looking at the microstructure of the lung using this technology. And so what we're interested in here is looking at how the microstructure, the alveoli in the lung, affect the diffusion of the gas atoms. And just to be clear, in case some of you do respiratory physiology, what we're talking about here is a random Brownian motion of the gas atoms, analogous when we do diffusion measurements, say, in proton MRI, not the transmembrane gas diffusion, which is what you look at with the pulmonary function test, DLCO. And analogous to proton MRI, what we can get from this is a quantitative measure. In this case, it tells us something about the airspace size and the airspace connectivity, and we get, just like in proton MRI, an ADC or an apparent diffusion coefficient. So qualitatively, we can think about this in the following. We have here a diagram showing a healthy alveolar sac. These little guys here, the alveoli, as compared to an emphysematous lung where the walls between the alveoli have been destroyed. So if we think qualitatively about putting a helium atom in there, if it's in a healthy alveoli, it's going to tend to bounce around and run into the walls as it diffuses. And this will give us a relatively low apparent diffusion coefficient, or ADC. On the other hand, if we think about an atom diffusing in this diseased alveolar sac, it's going to be to move around much more easily, and so it's going to give us a relatively high ADC. Here's a good example of how that works. On the left, we see a CT of a subject that had a lung transplant. We can see much more of the lung tissue. It's got a higher intensity on this side. This is the transplanted lung that's healthy. We see lower signal here because there's been a lot of tissue destruction due to emphysema. And now if we look at the ADC map for this subject, we see relatively low uniform values in the transplanted side. This reflects low ADC values because of the small, healthy alveoli, whereas on the left side of this picture, we see elevated ADC values. They're higher because we have larger airspaces due to the tissue destruction. Now, diffusion imaging has been applied to a number of diseases, including COPD and asthma, as we mentioned in the motivation section, also transplant lung development. Now, what I want to do for the next few slides is not go directly through these, but I'll show you results from a number of these as I talk about a few more of the technical issues involved with diffusion imaging that are important. So one thing that we really want to be concerned with is the diffusion time. That is how long we let the atom diffuse before we make the next measurement to see what happened. And the reason this is important is because the lung is fundamentally a complex branching structure. And this is illustrated in the diagram here on the right from Weibel. It's got approximately 24 generations of branching that have a wide range of sizes, all the way from about 20 millimeters in the trachea down to a few hundred microns in the alveoli. And we can get a feel for what this means if we look at how far the atoms can diffuse during the time period that we let them. So here we have diffusion time plotted between 1/10 of a millisecond up to 10 seconds, and this is the maximum mean or RMS distance a helium atom in air could diffuse if it were allowed to diffuse freely over that time period. So it's the maximum possible expiration. We see that if the diffusion time is quite short, on the order of a millisecond or so it should be able to explore just the alveoli, but not much further, whereas it can explore larger and larger structures, say up to the acini, if we let it diffuse for maybe 100 milliseconds or a second or so. So these considerations have been important in designing the techniques we use to do this, because the diffusion time determines which lung structures are probed by the diffusion measurement. So this has led so far in the development of this technology to two common diffusion implementations. The so-called short time scale measurements. These are measurements where the diffusion time is on the order of a millisecond or a few milliseconds based on gradient echo MRI pulse sequences. And so-called long time scale measurements, these where the diffusion time is up to on the order of a second or so. And these are based on what we call the stimulated echo MRI pulse sequences. Now, first I want to look at this first one. It's where we sensitize the measurement to diffusion along one direction, and we acquire two diffusion weightings, that is two images with different sensitization to diffusion, or for those of you who do diffusion imaging, you know this is called 2B values for the diffusion measurement. This is the one that's been done most commonly by many different research sites. And so what's been shown about this measurement is that it's exquisitely sensitive to the microstructural status of the lung. And there's some very interesting things you can see with it. For example, you can see the posture-related gradients in the alveolar size. That is, if, for example, the patient's laying on the table, their alveoli are a little bit bigger at the top of the lung than the bottom of the lung because of gravity pulling on the lung tissue. For example, we look here. Here's where they're laying on their side. The table is right here. Gravity's pulling the lung down. We note that the ADC values are much lower down in red here at the bottom of the lung, or this side of the lung, than at the top because of the gravitational gradient of alveolar size. It's been shown that this method is sensitive to detect subclinical emphysematous changes in asymptomatic smokers. Asymptomatic means these subjects have normal spirometry, and also in this study have normal CT. You look at their CT and you can't see any evidence of lung disease, but they can have quite elevated values in their ADC compared to age-matched normal controls. So we can see disease potentially with this method before we can see it in other ways. This technology can also detect the normal increase in alveolar size with lung growth. For example, we look here on the right. This is a graph of the mean ADC in the lung versus age. We see that it gradually goes up both with lung development and then with aging. Your alveoli slowly get bigger and bigger, or maybe some tissue destruction is involved at the older years. And on the left, we have a specific example. Here's a child about 9 years old compared to a 20-some-year-old. And you can see that the ADC values are much lower in the child, reflecting the smaller alveoli in the child, which get bigger as your body develops. Now, there is more information to be gained, analogous to proton MRI, for those of you who do diffusion with proton MRI. If you take not just two diffusion sensitizations, but multiple ones, that is, multiple B values. Once you have this data, there's a number of different ways that the researchers have looked at this to analyze the data, and I just want to show an example from one of these. This is where you use a geometric model to derive additional information from the information that you get with multiple B values. This is some work from Washington University, and what they did was model the functional lung units as a so-called alveolar sleeve. It's essentially a tube with alveoli on the outside of it, and then you can make this into a specific geometrical model. And if you take the data from multiple B-value measurements, you can estimate the diffusion along the sleeve and perpendicular to the sleeve, and then from these numbers you can estimate these geometric parameters, the diameter of the sleeve, how big your model alveoli are, how deep they are, and so forth. And then what's even more interesting is you can take this geometric data and then calculate things of physiological relevance. For example, you can estimate the surface to volume ratio of the lung, the alveolar density, and things like the mean linear intercept. This is a measure that's used in histology commonly to quantify the status of the lung. It's important because then you can compare these measurements to histological measurements of the lung. This model has been used both in animal studies and lung specimens with comparison to histology, and it seems to give quite reasonable values compared to what you get from histology. And I just want to show an example here. Here's the model applied in human lungs. This particular figure shows a former smoker which has normal spirometry compared to an active smoker in a person with moderate COPD. And what we see that each of these parameters tends to worsen as we go from the essentially normal person up to the person with moderate COPD. In particular, if we look at the alveolar depth, this is the size of the walls in the alveoli. We see that this goes down quite a bit in the COPD subject. So what's this saying is that the alveolar walls are being destroyed due to the disease process. And so this is interesting both that you can see the effects, but you can also get quantitative numbers which are meaningful to someone like the lung physiologist. Lastly, microstructure, I'd like to briefly mention these long time scale measurements. That's when the diffusion time is quite a bit longer. So at least in principle, the gas gets to probe much longer length scales and maybe look at different information within the lung. Here's an example. We have a healthy subject and a subject with mild chronic obstructive pulmonary disease. We see the healthy subject for diffusion time of 1.5 seconds has low and uniform ADC values, whereas they're overall elevated in this subject with mild COPD, and they're much higher in the apices, which is a finding that we often see. Now, what's interesting about this is if you compare this to a short time scale map, this is similar to the types of images I showed in the last few slides. What we find is that the elevation between the center of the lung and the apices is quite twice as big for the long time scale than it is in the short time scale. So this suggests that perhaps this way of looking at the ADC values may be more sensitive to early changes that occur in emphysema. And perhaps these are looking more so at connectivity than they are tissue destruction. Probably perhaps the tissue destruction is not as advanced yet. And one last example of this is an interesting study that was done looking at people exposed to secondhand smoke. So what we have is a group that had low exposure, that weren't exposed to smoke much in their life. With high exposure, this is like you grew up with a smoker or you worked for many years in an office with a smoker, and then compare those to people that were active smokers. We see an overall increase, general trend of increasing in these long time scale ADC values as you go from low exposure to high exposure to smoking. And if we look at some specific cases here, here's a representative low exposure person. They have relatively low uniform values, both at the short time scale and the long time scale. But if we look at a high exposure subject, we both see an overall elevation. These colors are a bit brighter on the scale. But we also see that the changes, you can see them in the short time scale, but they seem to be much more prominent in the long time scale than the short time scale. Again, perhaps greater sensitivity to some of these early changes to smoking damage. And if we look at a smoker, we see what we'd expect. We see obvious changes in the short time scale ADC map, and in changes in the same region, but more pronounced in the long time scale ADC map. So overall, what I hoped I sort of told you about during this section is that hyperpolarized-gas MRI provides several unique approaches for regional quantification of both lung function and lung structure. And this technology would seem to have a number of obvious applications for disease detection, monitoring of disease, and assessment of new therapeutic drugs. So this all looks very promising, but there is a practical problem. And that's a practical problem I'd like to talk about in the next section. And this is the supply of helium. And what I'd like to answer in this short section is, what do nuclear weapons, terrorism, and hyperpolarized gas lung imaging have in common? So earlier in the talk, I told you that helium-3 comes from the decay of tritium. And tritium has about a 12-year half-life. What I didn't mention is that probably the biggest use of tritium is that it's a key component in nuclear weapons. And in fact, essentially all of the helium-3 that's been used in the lung imaging research that I've told you about and has been done at the many sites, or a number of sites around the world at least, has come from tritium that was formerly in nuclear warheads. A lot of this has come from the former Soviet Union, and also some of it come from the United States. Now, even though that's the case, up until recently, this material was quite reasonably priced. You could buy a liter of helium, for which you could do several studies, for a little bit over $100 a liter. Now, in order to understand what's happened, it's important to look at the competing uses for helium-3 aside from nuclear weapons. So helium-3 is very important for a number of basic physics experiments, including experiments in nuclear physics and low-temperature physics. It's used in probes for oil and gas exploration. And the most important thing for our purposes is that it's used for neutron detectors to try to detect covert nuclear materials in a device sort of like the one we show here on the lower right for port and border security. This is the one that became very important a few years ago. And to understand this, here's a plot of at least the amount of helium-3 that's been in the U.S. stockpile over the last 20 years. What we see in red is the size of the stockpile. In blue, disbursements are used from the stockpile, and then additions to the stockpile from decay of tritium, where they take the gas out of the nuclear warheads and put it into the stockpile. What we notice is that a very sharp decline happened right about here. And this is not a coincidence. It coincided with the terrorist attacks of 9/11. What happened after those terrorist attacks is that there was a significantly increased use of helium-3 and these neutron detectors for port and border security. And that started drastically drawing down the stockpile. And in fact, the folks that watched this kind of thing weren't really paying attention for a few years until the stockpile started to get quite low, and they noticed that things were heading to where there would be no helium-3 left. And they, in fact, stopped the use of helium-3 briefly right around this period until they figured out what to do. And so what has happened now, what I think of as a new reality, is that it's much harder to get helium-3. The helium-3 from the U.S. supplies is being rationed by the Department of Energy among the different people that need to use helium-3 because of its unique properties. There is a specific allotment for medical imaging research. It's around 2,000 liters per year. I think it's maybe something like 1,800 liters this year. And the price is much higher than it used to be. You remember I told you it was around, say, $100, $125 a few years ago. Now the price is just under $800 a liter, but this is in fact subsidized. The free market price of helium right now is something like $2,000 or $3,000 a liter. And obviously, if you look at these supplies, what we take away from this is that if this technology, specifically hyperpolarized gas imaging using helium-3, is to become widespread, we need another supply of helium, or helium-3. There are a number of different places this may come from, but right now it's not real certain exactly what will happen. One of the most interesting ones, you may have heard about this, is getting it from the moon. In fact, there's a lot of helium-3 in the soil of the moon, but that's probably a long-term and very expensive proposal. And so the second thing this does is makes us look harder at the alternative agent I mentioned, that is xenon-129. And so the next section of my talk is to say, well, can xenon-29 come to the rescue? Or put another way, is it a viable replacement for the types of procedures I've showed you early in the talk that were developed originally primarily based on helium-3? So to answer this question, it's useful to first look at some of the properties, how they compare between xenon and helium. One very important property when you're doing MR, of course, is the so-called gamma or gyromagnetic ratio, which is about 3 times larger for helium than for xenon. This tells us how big the magnetic moment is and how big the signal is we'll get. And so our signal to noise is fundamentally lower for xenon because of its lower value of gamma. That means that it's critical to have high gas polarization when we're using xenon-129. Now, the diffusivities of both of these are quite high because they're gases. This is about 10 to the 5th times larger than the diffusivity of water molecules in biological tissue. But even so, because xenon's a relatively large atom, its diffusivity is about 9 times less dilute in air than helium's is. So I showed you some very interesting results 2 sections ago about looking at the microstructure with helium-3. So an obvious question is, given this big difference, can we get comparable information with xenon-129? An accessory question is, well, since it's a lot less, maybe it can allow us to probe things that we can't do with helium. So those are things that need to be looked at and answered. Another important issue is polarization. Now, helium-3, because of the physics of the polarization process, is just easier to polarize. In fact, for many years, people have been getting polarizations on the order of 50% with helium-3. But historically, the polarizations for xenon-129 have been much less, only about 10%. Given its fundamentally lower signal, it's very important to get this up. And actually, this is one thing that has been addressed in just the past couple years. And there's one person, Bill Hersman, up at the University of New Hampshire, has done a lot of work on improving the xenon polarization. And through a startup company, they have some initial products. This is an example of one of them that can get quite good polarizations with xenon. This particular system can deliver a couple liters in a run which takes about 30 minutes, which is plenty of gas to do several human experiments. And it can get polarizations up to about 50%, which is critical if xenon is going to try to replace helium. So we're ready now to take the first stab at this and say, well, can xenon do good compared to helium? And the best way to try to convince you is show you images. So here's some ventilation images in a healthy subject, top row with helium-3, bottom row with xenon-129. And I think you can tell by looking at the images that the xenon-129 results look quite good. They're quite comparable to the helium images. Here's some xenon-129 results of ventilation and disease. We have an asthma subject, a COPD subject, and one with cystic fibrosis. I hope you'll agree that these images look quite comparable to the ones I showed you in the section with helium, and so we seem to get good results for this. And the last thing I wanted to mention on this topic was ADC. We showed some very interesting results looking at the microstructure using diffusion measurements with helium-3. This shows an early comparison between xenon-129 and helium-3. These are different subjects, but the same classes of subjects. So we compare healthy and a COPD for both gases. In the healthy case, we both see relatively low and uniform diffusion values. COPD, we see focal elevations of much larger. And so we seem to get very comparable results, although, of course, a lot more work needs to do to flesh this out and to see what the real detailed differences are. But the interesting thing about xenon, aside from just doing what helium does, is it has some unique properties which let us do more and look at different things. So one very important thing is that xenon likes to dissolve in stuff, particularly tissues with lipids in them, whereas the solubility in biological tissue of helium is quite small, essentially negligible. So what this means, and we'll look at this in the next couple slides, that we can use xenon to probe pulmonary gas exchange. An accessory characteristic which is important in doing this is that xenon, because it's a big atom with a really big electron cloud, and that gets distorted as it goes into materials, it's very sensitive to its local environment. And what happens is when xenon, for example, goes from the air spaces and dissolves as something, that it has a very big, what's called chemical shift. What this means is the signal coming from the xenon changes dramatically when it dissolves. And then that lets us figure out where it is because of its frequency. So if we keep these properties in mind, let's look at what happens in a little bit more detail when you inhale xenon. So when you inhale hyperpolarized xenon, of course, it goes into the air spaces amongst the alveoli, and it also dissolves in the lung parenchyma, in the plasma, in the red blood cells. Now, if we were to acquire an MR spectrum of that xenon in the lung, we'll get something like this. What we see is a very large peak at the frequency corresponding to the xenon in the air spaces, but we see two smaller peaks over here on the right for the xenon that's in the lung parenchyma and another distinct peak from the xenon in the red blood cells. So importantly, we can see it in these compartments, and we know it's there because its frequency, its chemical shift or frequency is much different from the xenon in the air spaces. And this difference is quite large. In fact, at 1.5 Tesla, it's a little bit bigger than 3,500 hertz. So it's a difference that's very easy to detect. Much bigger, for example, those of you who do proton MRI, this shift is about 60 times bigger than the fat water shift for proton MRI. So it's very easy to distinguish these things. So if we look at how much we have, most of the xenon resides in the air spaces. About 98% in any given instance is in the air spaces. We often call this the gas phase. This is what we use to do ventilation imaging or diffusion imaging or the other things I talked about with helium. There's a small but not negligible fraction that's dissolved into tissue and red blood cells. This is about 2%. We often call this the dissolve phase, and we can use this to look at gas uptake or gas exchange. Another important aspect of this is that when you breathe in the xenon, it doesn't simply go into the tissue and the red blood cells and gets carried away. Well, some of it obviously does. But there is this ongoing dynamic exchange driven by diffusion where the xenon moves back and forth between the air spaces in the tissue and red blood cells. And this is a very important aspect of it where we can design techniques to look at the gas exchange processes in the lung. And because of this exchange, it permits two distinct alternatives for looking at gas uptake or gas exchange in the lung. There's a so-called indirect imaging approach, which is based on this dynamic exchange. If we design the acquisition properly, we can make it so that the signal in the gas phase is inversely related to how much exchange is going on between the air spaces and the tissue. There's a method that takes advantage of this called ecstasy. That's the acronym for it, so-called xenon polarization transfer contrast. And then, of course, we can look at it directly because the frequency of the signal is much different. We can just image at that frequency. The disadvantage of this compared to indirect imaging is that the spatial resolution is limited because of the low fraction of xenon that's dissolved. But we can nonetheless get some interesting results with this approach. Here's a diagram that tries to give you the major features of this indirect imaging, or so-called ecstasy. So the idea behind this is that we start out by acquiring an image of the gas in the air spaces of the lung. And then we manipulate the magnetization within the dissolved phase compartments. Specifically, what we want to do is apply RF, or radio frequency pulses, to the magnetization that's in the lung parenchyma and the red blood cells, and essentially destroy that magnetization. Now, that's illustrated on the plot on the right. We can destroy it, but then due to exchange, it will grow back. So it grows back in those two compartments, but as it grows back, it's taking away the signal or the magnetization from the gas phase. Now, for one pulse, this is quite small, but we can amplify it by just doing this a bunch of times. So if we continue to periodically apply RF pulses to the dissolved phase, we'll draw down the gas phase, but we'll draw it down based on how much exchange there is. So we'll make it go down a lot if there's a lot of exchange and not so much if there isn't. So this tells us about the gas exchange properties locally. And after we've applied a number of these pulses, what we could think of as contrast generating pulses, then we take another image, and from these two images we can form a map which tells us about the gas exchange in the lung. Another detail of this is that the actual properties of the gas exchange we look at can be manipulated by the spacing between these pulses. So we can pull out different properties of the gas exchange by doing experiments with different spacings between those pulses, those RF pulses. This shows you an example of some results from this. These are some so-called ecstasy experiments that were done in two human subjects. We have a healthy subject and a subject with COPD. And they were done with multiple different time delays for those contrast-generating pulses, so we can pull out some parameters of physiologic interest. Specifically, we have maps that reflect the tissue density in the lung and that reflect the septal wall thickness. That's the thickness of the wall between, say, two alveoli where the gas exchange is taking place. What we see, if we look at the healthy subject, is that within the plane it's fairly uniform, but the tissue density gets much higher toward the back of the lung. This is the same effect we saw with diffusion imaging, where the ADC values were low at the back of the lung, because the subject's lying on the table, gravity's pulling their lung down, so their tissue density is higher at the back because they're laying on the patient table in an MRI scanner. If we look at the COPD subject, we see the same general overall feature, but we also see these areas, for example, here and here and here, where the signal is much lower. This, in fact, corresponds to places where they have emphysema and there's been tissue destruction. In this particular subject, I don't have it on the slide, but it was confirmed both by ADC measurements and by CT in this subject that these correspond exactly to where there's tissue destruction from emphysema. Now, if we look at the septal wall thickness measurements, the overall behavior here is analogous to what we saw at the tissue density. We have compression of the lung and thickening of the septal wall at the back of the lung due to gravity. But what's very interesting is if we look at the COPD subject. Now, even though this subject has, for example, tissue destruction in some areas, we see that overall their septal wall thickness is elevated throughout the lung. And what this should indicate, although it's not been proven, this probably indicates inflammation, which has made the septal walls thicker throughout the lung in the subject with COPD. Now, for the last xenon thing I want to mention, let's look briefly at this direct imaging of gas uptake. This is something that was looked at early in the development, but it was difficult because of the relatively low polarizations and low quantities that were available at the time. Over the past several years, there's been a lot more effort put into this, and some interesting results have started to come out. Now, the gas exchange that happens between the air spaces and the parenchyma and red blood cells is also very important for this method. It's important because the gas phase continues to replenish the dissolved phase compartments, even if you use up the signal in the dissolved phase compartments. So what that lets you do is to use a high degree of excitation, or in MR what we call high flip angles, to get a big signal, as big as we can, from the dissolved phase compartments, and then wait a little bit, and then let it be replenished by the gas phase. So it lets us do better than you might think you could if you just said, oh, there's only 1 or 2% there. How are you going to make a decent image out of that? Here's an example from this type of imaging. This is a particular implementation where we've taken advantage of the frequency difference between the gas and the dissolved compartments in order to get both images at the same time, where on one side we have the gas phase and next to it we have the dissolved phase. And that's what we see in the image. This is one image where we have gas phase xenon on the left, and we see fairly uniform because this is a healthy subject. And we see the dissolved phase, or this is reflecting the gas uptake into the lung tissue, on the right. And again, since this is a healthy subject, we see uniform gas uptake, which is what we would expect. Now, in this slide, we show an example of a 3D implementation of this type of imaging, comparing a healthy subject to a subject with mild COPD. If we look at the healthy subject, the main feature we see is a gradual increase toward the back. This is reflecting the same feature we saw in the ecstasy images, and the same thing we saw in the diffusion, is that because of gravitational tissue compression, we have more tissue here at the back, and that's why we see a higher signal. Now, if we look at the COPD subject, aside from seeing ventilation defects throughout the lung, which is what we expect to see in someone with COPD, we also see that their dissolved phase signal is quite a bit higher in the anterior portions of the lung. And this is really pronounced if you look at the ratio of the dissolved phase signal to the gas phase signal. We see that these values here are much higher, yellow, compared to the healthy subject. And again, what we think we're seeing here is a reflection of inflammation. We're seeing a higher dissolved phase signal because of the inflammation in the tissue. We do see areas where the signal tends to drop out, for example, at these arrowheads. But if we compare these images to ADC images that were acquired in the same subject, we see that these areas very closely correspond to places where the ADC is elevated. So you would speculate that the reason you see the drops in those places is because there was tissue destruction and therefore less tissue for the gas to be uptaken. Okay, to summarize this section, what I've hoped that I've showed you is that with Xenon 129, we can get comparable results for the techniques that were pioneered with helium-3, such as ventilation imaging and ADC imaging. And in fact, Xenon can actually add more value than helium itself because it lets us look quantitatively at either gas exchange or gas uptake in the lung. Now, the next topic I wanted to touch upon, getting close to the end here, is dissemination, or maybe lack of dissemination. Because if anyone here has actually looked at this field, a logical question you might ask is, if this technology is so valuable, and if it's been around for about 15 years, why isn't it being used at my institution or at more institutions? And that's an important and very legitimate question. And so in order to answer this question, let's look first at what you need to do this. What do you need to do hyperpolarized-gas MRI? Well, you need an MR scanner with a multinuclear option. This is fairly common. A lot of MRI vendors you can buy this from. You need specialized coils, but again, you can either build these or you can buy these from multiple vendors. The real important point is this last one. You need a gas polarization system, and the important part is historically you have not been able to buy these. And so then the question comes, why have you not been able to buy these? Well, one of the very big issues is involved with intellectual property and patents. This is a couple of snapshots out of a patent that was filed by the people who first demonstrated this technology. And what I've highlighted here on the right is the first claim in the patent. And basically this says you administer hyperpolarized gas, you detect the signal and make an image. And that's the claim. I mean, that's as broad as a claim can be. It's basically in vivo MRI with hyperpolarized gases is the claim that they got granted in this patent. So as I said, it's important. It's extremely broad. The second important thing is that this patent was exclusively licensed to a company. And what it means is whoever had this patent controlled the field. So what happened, if we look at a brief timeline here, is a company, this was a startup company formed in the mid-1990s called MIDI. And what was good about that company, it was a small startup company, and their business was to sell and service polarizers. So this seems good. You can buy a polarizer, you can investigate this field, see if you think it's something that's worthwhile. But what's bad is they didn't exist very long before they were bought by a drug company, Nycom and Amersham Imaging, which then became Amersham Health, and then Amersham Health was bought by GE in 2004. The bad part for the field is during this time period, polarizers were not sold. There were a small number of polarizers on loan from these companies, a handful of academic sites and some pharma companies, but they had substantial use restrictions on them. Some sites built their own polarizers, Polarizers are somewhat complex, and you need special expertise, so not everybody would want to build their own polarizer. Another issue is these IP issues with the field still remain, even if you build your own polarizer, but I don't have time to get into the details. But basically what happened is during most of the life of the field, the dissemination of this technology is stagnated because of the practices and the patents that were involved. What's very important is something that happened just last month. Just last month, a new company was formed called Polarion. And in fact, this company reformed in the same physical space where MIDI originally existed. They acquired the assets and intellectual property rights from GE Healthcare, and now they're in the business of selling and servicing polarizers. In fact, they've already got orders for a handful of polarizers over the past couple weeks, and so now it is again possible for you to buy a polarizer and explore this technology if you think it's interesting to you. So if we give a summary of this, patent and commercial issues blocked the open dissemination of this technology for almost its whole life, from the late 1990s till December of 2011. But now, as of last month, it's possible to buy a commercial polarization system from a company and have the right to use it. Now, there's another very important point, and I don't have time to get into it, but I just want to mention it, and we can talk about it later if you're interested, is that both of these agents are classified as drugs. That's important in the development, and it's also important. It's why you could build your own polarizer and use it and not get sued, but you really had to be careful what you were doing. But we can talk about that offline if you'd like to. So the final thing I'd like to do is make a few comments about quantification. Now, I'm not going to give an overview of what's been done in this field, really, because we have several talks in this workshop that will go into that. I just wanted to give you, sort of a high-level view of as a person that develops the acquisition side, what I think about quantification. So first thing I'd like to say, or how we should think about this, is how should these imaging results be processed or packaged so we can present them to the broader medical community, say to pulmonologists and the clinical physicians. And to look at this, first we have to recognize that there's a number of technical challenges with this that may not exist for some of the other modalities. We know that some of these things are common with proton MRI. For example, one of the big things about proton MRI in certain instances is that the signal has arbitrary units, unlike CT, which is fundamentally quantitative. We have to live with these spatial variations of the receiver coil sensitivity in MRI, and those have to be corrected, which is often thought of as a bias correction for the images. We also have to, but we have to deal with this, all modalities. If we're doing longitudinal studies, we have movement among the time points, but for many applications, for example, the brain, this is a rigid motion, which is fairly easy to deal with. So we're hyperpolarized-gas MRI. We have all of these, but we also have the fact that the signal strength fundamentally varies among time points. That's because the signal comes from your polarization level, which may vary, and the dose, how much gas you give the patient. So the signal level you get in one experiment, you might do the exact same thing, and it could be 50% different. And so that's a problem. We have an additional spatial variation because the body coils in the scanners can't be used. You have to use a dedicated transmitter coil, which is often close-fitting, which means the degree of excitation or the B1 field varies across the subject, and so that can lead to contrast changes across the image. By its nature, the size and shape of the lung vary among time points. So this is a challenging thing that you have to deal with and have to find a way to do effectively. Again, due to the nature of the lung, unlike, say, for example, the brain, you don't have a lot of anatomical landmarks in these hyperpolarized gas images to know what things should look like in advance. So you have little prior anatomical context for your image processing. And a final point I've listed here is that the disease contrast can be quite complex in some of these instances compared to a normal subject. It can be really hard to figure out, what you're really looking for. This is the image I showed earlier from a cystic fibrosis subject, and I just want to look at this again. I think you can look at these middle images and you can see there's regions that maybe look pretty normal and maybe there's a ventilation defect here, but in these original images, I think it's quite challenging to figure out really what's healthy and what's not healthy. It's much more difficult than a tumor sitting in the brain. This is a much more complex situation. Now, this field, the quantification of these images, is really in the early stages of development compared to other fields like looking at MRI brain images. But there have been some efforts put forth. One of the earliest things that was done was just to count ventilation defects and quantify things that way. This can be useful, but for example, in a case like this, I would propose it's actually quite useless to try to count ventilation defects. You won't get a reproducible answer. Another thing that's been looked at a lot is trying to quantify the ventilation defect volume or the percentage of the lung that has defects. There's also been some initial attempts at looking at texture heterogeneity measurements, which I think are very important, but we're still in the very early stages there. ADC measurements have shown a lot of very interesting information, so it's good to look at what's been done there. Mostly what's been done is just summary statistics, like looking at the mean value or the standard deviation or perhaps gradients from the front of the lung to the back of the lung or the top to the bottom. While this is useful, we really need to go a lot further than this. There's also been some initial attempts at looking at texture or heterogeneity of the ADC values. This is just an example of one of the types of things that's been done in trying to quantify the hyperpolarized gas ventilation lung images. Some work from Nick Tustison in our group and co-moderator. He shows the use of using several different subjects to form an unbiased template and then build a statistical model of the lung shape and then use this group knowledge together with individual subjects following bias correction to try to classify the lung defects into several different classes, which can be useful as opposed to just trying to say defect, no defect. I mean, you really need to grade them in some way because it's not as simple as defect and no defect. And I'd like to end by giving a very high-level view from a developer standpoint of really what's needed along the quantification lines and where we need to go over the next several years. Well, the first point is important but probably very obvious. These images are so complicated that what you really need is an automated, robust method for doing it, not something that involves operation intervention. And I think this is going to be important for this technology to really get used clinically in a wide sense. I think it's important for us to move beyond global summary measures, like particularly with ADC when using mean ADC or total defect volume for the whole lung. While this is important in some contexts, we really need measures that portray the richness of the underlying images, because if we don't, it's really going to hurt the field. We don't want to end up having these beautiful images and then distill it down to one number like spirometry. If you want one number like spirometry, you just do spirometry. It's a lot cheaper. And lastly, this is something that's also very important but obvious. We need to correlate and validate these measures with independent measures of function, structure, disease. While this seems obvious, it's actually quite difficult because many of the approaches with hyperpolarized gas imaging provide things we haven't been able to get before. And so when you have new things, it's always a trouble of how do you say that that's really telling you what you think it is. But that's important for the clinician or the pulmonologist to accept this technology. So in closing, I'd like to give a very high-level summary of what I went over. First major point is that lung disease is a major worldwide health issue with great societal impact, and we really need to develop better technologies to help address that. I hope I've convinced you that hyperpolarized gas MRI offers a wide range of unique ways to get functional and structural information about both the healthy lung and the diseased lung. And what's very important for the field, but has nothing to do directly with the technology development, is that it's only now possible to have open dissemination of this technology. And this is going to be very important, of course, to see if this can disseminate among other sites and really assess the potential value of this technology. And just as important with this is developing proper quantitative methods that go along with the technology to see its value. So let me just close with my opening slide, and I asked this question in my title. And actually I haven't answered this question because I can't answer it yet. But hopefully what I did show you is that this technology has a lot of research potential, and at least in my eyes, it has a lot of ability to translate to the clinic. Now that you can actually buy polarization systems, you can go out and test the technology yourself, hopefully we'll see that this very interesting technology can translate into clinical application over the next 5 or 10 years. Thank you for your attention.